Hello, everyone, and glad you're here and hope you all had a good summer. Although it's not the first time we have the meetings that happen this academic year, but this is the first lunch meeting. Of course, our signature CCSS lunch meetings. Please come in, we just started. You can grab some lunch outside. I send him back again. And but today we're very happy to have Arjan here. That's our first lunch meeting guest to kick off this year's thing. So Professor Dr. Arjan van der Schaft and received his Ph.D. degrees in mathematics from the University of Groningen in 1983. In 1982, he joined the Department of Applied Mathematics at the University of Twente, where he was appointed as a full professor in mathematical systems and control theory in 2000s. In September 2005, he returned to Groningen as a full professor in mathematics. So Arjan has a lot of titles and positions, like he is a fellow of the IEEE, that's the Institute of Electronical and Electronics Engineers, and a fellow of the International Federations of Automatic Control. Is also a member of, you can see from here now, that's Brunoni Institute for Mathematics, Computer Science, and AI, and also Young C. Willems Center for Systems and Controls. And of course, and he's also the author of multiple books. All in all, what I wanted to read out loud all these titles and positions, just want to show he's the expert in nonlinear control systems, and he's the right person to kick off this year's new themes of CCS lunch meeting. That is the control of the complex systems. So, floor is yours.
Okay, thank you very much, and thank you for the invitation, for being here and giving this talk. Okay, so I will talk, well, I mean, the title over there is already complex, so that you should be okay here. Okay, I do not know very well the audience here, so please, if there are questions or comments during the talk, just ask them right away, so we can keep it as informal as possible. Okay. Just use it. Okay, so I will talk about in the framework for the modeling, control, and simulation of complex systems. It's called Port-Hamiltonian system theory. And the name comes from the fact that it is combining, well, three scientific traditions. So, first of all, classical mechanics, and especially the coordinate-free formulation of Hamiltonian dynamics, where you model this by a geometric structure, which is typically called a symplectic structure on the phase space of the system, and so the configuration coordinates and the momenta. Secondly, the total energy or the Hamiltonian. So you do not consider general differential equation, but you write it. You first identify an underlying geometric structure of the phase space, and the total energy. Okay, and secondly, there is the network tradition, which largely comes from electrical circuits, where you look at your circuits as being composed of ideal components, like capacitors, inductors, resistors, and they are then linked by a Kirchhoff's current and voltage source. Yeah, so that's the network point of view where you are talking about ideal components and putting them together. And then thirdly, I could also add resistors and control over here, because that is from the very start, it is considering open systems. Yeah, so systems which can interact with the environment, and where you can also put extra components and particular controller systems in order to influence the dynamics of the system. And there are many applications throughout engineering, complex technological systems, like the ones indicated over there. And also in natural systems, in particular systems biology, synthetic biology, and other areas. So in circuit theory, there you have your network structure, which is being captured by Kirchhoff's current and voltage laws, and the graph of the topology of the circuit graph. Also in the infinite dimensional case, so if you are considering PDEs, then you have also something similar, but these are then typically called balance laws, but they play a similar role as network structure. In some sense, you have an infinite dimensional version of it, which is in the case, for instance, of Maxwell's equations, which are Ampere's law, where, okay, not bother too much about what all these quantities are, and Faraday law. And so you can compare them with the current law and the voltage. Okay. Now the idea of Port-Hamiltonian system theory is that you combine these ideas, and you in particular you emphasize the concepts of power and energy. Yeah, so you look at your complex system as being composed of ideal components. Yeah, and these ideal components, they are being divided into three groups. There is pure energy storage, like in the circuit case, electrical circuit case, capacitors and inductors. There are power routing elements, which are just transforming power in a power conserving way. And there are pure energy dissipating elements, like resistors in the electrical circuits. And all these ideal components are being interconnected, like in the circuit case, by conjugate pairs of variables, which we will denote by F and E, whose product is power. Yeah, so again, think of Kirchhoff's current and voltage laws. Okay, so I should point out one caveat over here. So if I'm talking, so throughout, I will be talking about pure energy dissipating elements. Well, of course, that is from a thermodynamics point of view, that is strange, because energy is then transformed into something like heat. Yeah, so what I will consider is the quite common case where the total energy is being split into an Hamiltonian, which is depending on the normal extensive variables like volume and so on, plus on the internal energy, yeah, which is only depending on the entropy. And that means that you indeed just have energy dissipation going out of the system, and you do not have to take that into account anymore, that energy. Yeah, but of course there are cases where this is not being satisfied. Okay, so the basic cartoon for Port-Hamiltonian systems is over here. Okay, so what do I mean by this? Well, okay, I put all my energy storing elements, I put them into this blue balloon. Yeah, storage, and I put all the energy dissipating elements like resistors or dampers in the mechanical case. I put them into this well, orange kind of balloon, let's put this like that. And then you have these E and F vectors, yeah, which are here being split into three classes corresponding to energy storage. Yeah, so they are linking the energy storage, and the ER corresponding to energy dissipation. And then we also have this open port over there. So that are the variables that can be interconnected to the environment, to the surroundings of the system, or to other systems. Yeah. And that central yellow object over there, that is a geometric structure comparable to the symplectic structure in classical mechanics, or Kirchhoff's and current laws again in the electrical case. That is linking all these E and F variables to each other, and like Kirchhoff's current laws and voltage laws are linking currents and voltages to each other. And this is power conserving, like Kirchhoff's laws are also. I mean, the total power, and so you write down Kirchhoff's current and voltage laws. And then if you look at the total power, that is zero. And so that is just distributing power from one component to another. So that is the framework that we take for modeling. Okay, this is especially suited for simulation of control purposes, I would say. I mean, it could be that people from physics that they do object, because what we are assuming here is that we can always make a separation between pure energy storage and pure energy dissipation, for example. Okay, I mean, so my background is control theory, and we deal with engineering systems, and there it is all perfectly fine. And so, I mean, modeling is, of course, something that people have different views on. And I mean, in applied mathematics or in engineering setting, then modeling, that is always an approximation of the reality. And while some people from physics would say that they are actually dealing with reality, they come up with a physical model, but that is not what I'm doing. Yeah? Okay, so the summary of this Port-Hamiltonian system theory or point-based modeling is over there. Yeah, so we have three classes of systems, and okay, should also say that since these power routing elements, since they are anyway power conserving, I just put them into the interconnection laws. And then I put this big yellow thing, which is capturing all the power conserving things. Yeah, so I have conjugate vector pairs F and E. Well, typically in some linear space, what we call the dimension, but there could be also other cases, so if are always linear spaces, but that is not necessarily R to the so much. Okay, coming back to this geometric structure, so this yellow thing in the middle. So I was saying that this is generalizing symplectic or the Poisson structure from classical mechanics or Kirchhoff's laws. So what do I mean by this? Well, the mathematical definition is over here. It's called the Dirac structure. So this is going back to work by people like Weinstein from the 1980s, trying to unify concepts of symplectic and Poisson structures in classical mechanics, actually. So in the constant linear algebraic case, it is very simple. So we have these two. So we have a linear space F, yeah, where the vectors little f live in, and then we take the dual space, yeah, and then the Dirac structure is a subspace of the product, such that, well, the vector product of E and F is 0, and that means power conservation. And furthermore, the dimension of D should be equal to the dimension of F. And actually, you can easily show that this is in fact the maximal dimension if you want property 1. Yeah. Okay, so you could also say a Dirac structure is a power conserving subspace which is maximally dimensioned. Yeah, and then simple example is the graph of an skew symmetric map. Yeah. So where I look at all the F and E, where F is the image of E under an skew symmetric map. Yeah, but there are many more or many other cases. An equivalent definition where I do not actually bother about this maximal dimension is as follows. Then I'm looking again at the product space F times E, and I define this somewhat strange bilinear form. Yeah. So I take two pairs of F and E vectors, and I define this, which is an indefinite bilinear form. And then the Dirac structure can be also seen to be a subspace which is equal to its own or the tockenhole complement. That's not the good terminology, so I'm using companion with respect to this indefinite inner product. Yeah? Okay. Okay, going back to this cartoon. So we have defined our Dirac structure. So this Dirac structure is involved in all the F's, so the F's corresponding to storage, dissipation, and the interaction ones, and same for E. Yeah, so this is linking all these variables in a power conserving way. And then what we do is that we then substitute for the definitions of energy storage. Now, energy storage, that means that we have in the Hamiltonian, which is corresponding to the total energy. And we put Fs to be minus x dot, so we integrate Fs, yeah, like in Kirchhoff's current laws, where we would integrate currents to charges, yeah. So and then the x factor that's going to be the state factor of the energy storage. So, okay, so we do that, and then we take any form of energy dissipation, and in fact, I should have added here something, because we cannot take any equations just linking FR and ER, but they should be such that for all solutions over there, I need the batteries. So for all FR, ER, satisfying those equations, that the power should be less than or equal than 0. So we have really energy dissipation. Yeah, and then we just take all the F vectors, so the one corresponding to storage, which is equal to minus x dot. FR, FP, and we take all the E's over there, yeah, and they should be for any time t, they should be in the Dirac sector, yeah. So the Dirac sector again, yeah, capturing how F and E are being interconnected, and then we still also have the energy dissipation equations. So in general, and that is a typical feature of network modeling, we do not get ODEs, but we get ODEs plus algebraic constraints. Yeah, so also called DAs. Yeah, so we get something more general, and then of course, and you can eliminate the algebraic constraints and then bring it back to the ODE case, but in fact, often that is not what you really would like to do, because it is, that can be very tedious and difficult, especially in nonlinear cases. And you lose all structure often. So what is very important about these Port-Hamiltonian systems is that they are compositional. So if you have one Port-Hamiltonian system, and if you interconnect it in a power conserving manner again to another Port-Hamiltonian system, then again this is Port-Hamiltonian. Yeah, so you can arbitrarily add components. And the Hamiltonian is very simple, that's just the sum. If I have n subsystems, it's just the sum of them. Yeah. The energy dissipation, I just take the product of them. And the trick is basically that if I take compositions of Dirac sectors, then we can prove that they are again Dirac sectors. Yeah. Okay, now, okay, this is of course, this is just for illustration purposes and just to understand the line on top. So this is the obvious linear mass spring system. So what more can we say about it? Well, okay, I'm looking at it in a slightly different way than within classical mechanics, because I say, well, so we have two energy storing elements in this case. So we have a spring, yeah, and then the x variable, the state variable, is the extension of the spring and the elongation of the spring. And then F and the E variable are the velocity and the force. Yeah. And I have a second energy storing element, which is a mass, yeah, which has energy, kinetic energy, of course, and then I have an FNE, with where in fact the interpretation is just reverse. Yeah? So the state is the momentum. And then, okay, so I have these two energy storing elements, and I link them by a Dirac structure, so this yellow thing. So I do not have energy dissipation. I could easily add that, then 10% is 1. But just for simplicity, I don't do that. And then the Dirac structure is just being given by some, well, 1, 2, 3 independent equations, linking these 6 variables in total. So I get the 3-dimensional subspace, which is maximal dimension, which is power conserving, as you can check. And then you get, well, of course, that is not a surprise, you get to the classical Hamiltonian equations, yeah, where the state vector is QD. But we also have an input, which is the external force in this case, and the output is the corresponding velocity of the mass. Yeah? Okay, well, this is more in a typical engineering example. Very simple again. If I look at the model of the DC motor, now then the standard model is being derived by saying, well, there are 5 subsystems, 2 energy storing elements again, and there is an inductor which is storing magnetic energy, and then there is rotational inertia. Yeah, so there is kinetic energy, and there are 2 energy dissipating elements, one in the electrical domain, one in the mechanical domain. By the way, this is the first multiphysics example. And so you see that you can easily combine, and in fact that is one of the origins of this theory, that you like to cover multiphysics systems within a common framework. Okay, and then there is a somewhat mysterious element, which is the gyrator, which is a power routing element. So it preserves energy, but in fact this is responsible for the transformation of magnetic energy into mechanical energy and conversion. Yeah. By the way, this is the model of a motor, but it is at the same time it's a model of a dynamo. Yeah, this is just how you use it. And so I have 2 external ports. There's an electrical port on the left-hand side, yeah, with a voltage and current, and I have a mechanical port on the right-hand side, with an angular torque and an angular velocity. Okay, and then I put everything together, and so I just take the linear case. I could actually look at nonlinear models. So at the bottom there is this energy routing gyrator. Okay, will not spend too much time on the details, but just to show the flavor of this type of modeling. So I have energy dissipation model there, just in a linear way, could be also done in a more complicated way. And then I have the Dirac structure, where I put all these things together. And then eventually, again, don't pay attention to the details, I get to a 2-dimensional state space model, where the energy variables are the magnetic flux of the inductor. So 1 energy storing element and the momentum of the rotating inertia. Yeah, and here you see a form which is quite often the case. So you have a skew symmetric part, yeah, which is power conserving. Yeah? The graph of skew symmetric mapping is the Dirac structure, and we have a positive semi-definite part which is corresponding to energy dissipation. And we have two inputs, which is the voltage and the angular torque. Yeah, so the two inputs from the electrical and the mechanical port, and we have the corresponding outputs, the current and the angular velocity. Okay, here you see that this is a conceptual way of modeling this system, because if you take a DC motor and if you open it, then you do not see this. So you, what you do is that you say, well, there is magnetic storage within, there is rotation all energy going in, yeah, and then you use this idealized modeling constructs in order to capture the dynamics of this. So, I mean, if you think about circuits, then we are, of course, used that you can just take the capacitors or the inductors from the shelf. But here you see that is not necessarily the case. And also in the circuit case, of course, if you take something from the shelf, these are also not ideal components. So these are idealized modeling constants. Okay, this is a bit similar, but much more complicated. Actually, this is because the phi s and the phi rho are both three-dimensional stator and rotor fluxes of a synchronous machine. So we have in total, we have the 8-dimensional dynamics over here. This is a bit similar to the DC motor, but there is an important difference because the coupling between the two physical domains, so mechanical, and so P and theta, okay, I should say what they are. Theta is the angle of the generator shaft, and P is the momentum. So these are the two mechanical coordinates, and we have 6 electrical components, and the coupling between them, which is essential because we want to either transform mechanical power into electrical power or the other way around, if we use it as a machine, is being given by that, or is being caused by the fact that the total energy, if you consider that first term over there, which is basically the magnetic energy, but you see that the 6x6 matrix L is also depending on the mechanical coordinates, the angle. And that is causing the coupling between the two domains. And that is causing the fact that these synchronous machines indeed do work. Yeah? Or generators, if you are converting mechanical work into electrical power. Okay, just as a short note, this can be also generalized to Dirac structures on the manifolds, and actually typically in 3D mechanical case that's also needed. So an example is where you are considering mechanical systems with kinematic constraints. So Q is again the vector of configuration coordinates, and then you get Hamiltonian equations with constraint forces. Yeah, so AQ times lambda. And then you get indeed that this Dirac structure is now modulated, so it depends on the state. Yeah, and then there is a whole theory about integrability, I mean, that's not really needed for the power conservation property, but it is needed for other things. So this is an example of this of such a kinematic constraint, the classical non-slipping of a wheel. In this case, a coin, a euro even, rolling on a plane. Okay, so comparing it to the classical mechanics setting, so you can say that we have done the following. So the classical mechanics setting is just the first part. X dot is equal to some symmetric matrix J. Yeah, this is called the Poisson structure, possibly depending on X, times the gradient vector of the total energy, Hamiltonian. So what we are doing is adding the possibility for energy dissipation, yeah, and we are adding the interaction with the environment, yeah, by which we can couple the system to other systems. Yeah? And in fact, we even get something more general than this, because in fact, as I was mentioning, the equations that we get typically also contain algebraic constraints. Yeah, so we get Hamiltonian DAEs with energy dissipation and with external force. Yeah, so we do not get energy conservation anymore. dBTH is not 0 because there is energy dissipation, and in fact there's also the interaction with the environment through which energy could go in or out. Yeah, so this is the summary so far. Let me check. Okay, we should speed up. Yeah, well, let me just say something more specific about the network case, and then I will leave out, I think, the PDE, the distributed parameter case. Let's just look at the network case. Yeah, so how can you write network models in a compact way? So I start with, again, with a very simple system example, mass spring damper systems. Well, what is the network? What is the underlying graph? Well, the masses, they are associated with the nodes of the graph, and both the springs and the dampers, they are associated with the edges of the graph. Yeah. Okay, first the node dampers. Well, then I associate to the nodes, I associate variables, which are the momenta in this case, and I associate the variables to the edges, which are the springs. Yeah, and then we get this dynamics where D is just the algebraic graph notion, namely it's the incidence matrix of the graph. Incidence matrix means that the j's column of D, that is corresponding to the j's edge of the graph, and this has exactly 1 minus 1, which is the starting node, and 1 plus 1, and which is the end node, and the other elements, they are 0. Yeah, so we get this Poisson Hamiltonian dynamics, where the Hamiltonian is just the kinetic energy plus potential energies corresponding to the springs. Yeah, okay, this is very simple, but you can generalize this. And if we add dampers, okay, then we get something similar. Then we split, and then we have columns of D corresponding to the springs and to the dampers. Yeah, and then we get this dynamics, which is again of the form that I showed before. Skew symmetric part and a positive semi-definite part. And again, this can be generalized. Now, okay, this is of course trivial from a mechanics point of view, but it's in fact also used in what they call consensus dynamics. What you get is that if you look at ddt of the total energy, kinetic plus potential, it's equal to that expression over there, where V is the vector of velocities of the masses, and LD is that thing over there. Yeah, so a positive semi-definite matrix, which, because of its special form, is also called the Laplacian matrix. And you see that you converge to the kernel of LD. Yeah. So to the situation where V is making the last term equal to 0. Well, if you have a connected network, that is just being equal to the span of the vector of all ones. Yeah. So you will converge always to this one-dimensional subspace. And where, in fact, you will converge to, that is depending on the initial condition. Yeah? Because there is also a conserved quantity, or called Casimir, and this is determining then what is the point in this one-dimensional subspace where you will converge. Okay, this is being formalized over here, but let's not. And then the statement is basically that you will converge. Well, when will you converge? Well, of course, you are depending on the dampers in your network, and because if there are none, then you have just pure oscillation. So you need enough dampers, or I should say, the dampers should be at the right location in the network. There should be enough of them in order that you will converge to this one-dimensional subspace. Okay, so you can also look at the out of equilibrium situation, and where you apply external forces, and then look at the steady states of the system. And you can do this same analysis, and then the Lyapunov function is now the shifted Hamiltonian. And then you can again show that you converge to the steady state if there is enough damping in the system. Okay, let me just, okay, this is the circuit case, which is a bit different, because in the circuit case, there all the elements they are being linked, or they're being attached to the edges. Yeah, so you not like in a mechanical case where the masses are sitting at the nodes of the graph. So you have to do it slightly differently, but quite similar. Now, third interesting case is our large-scale chemical reaction networks, and I was brought to this area by some work which we did some time ago in Groningen on the systems biology. where you have very large scale metabolic reaction network, and large scale means that it is not uncommon that you have, say, 500 chemical species and a similar amount of chemical reactions among them. Yeah, so in order to analyze them, then you have to, then you cannot just write down the equation and then hope for the best, but you have to do it in a good way. Okay, and in fact, it turns out that also in this case, you can come up with nice Port-Hamiltonian models. So, but okay, that is some story to it. So you start with the well-known stoichiometric matrix, and then you look at the underlying graph being defined by the left and right hand sides of the differential equation of the reactions, I should say. Yeah, so these are called chemical complexes. So that's defining again in the directed graph. There's an incidence matrix, but now you have another matrix Z popping up, which is specifying what are these complexes. And then you have to specify the reaction rates, yeah. And the most basic one is mass action kinetics. And then, okay, I will just go through this very quickly. But again, you will end up with a model. So the equations x dot is minus the matrix Z times some, well, a script L, which is again almost a Laplacian matrix. Yeah. It is not necessarily symmetric, but it has all the other properties. And then there is a somewhat ugly expression over there, where G is the Gibbs free energy, which is acting here as an Hamiltonian. And how should I look at this? Well, in fact, it is like a mass damper system, but then a damper which is very nonlinear. So, which is being given by the expression over there. But you can still prove the same dynamical phenomena as for mass damper systems. So you will converge to some, well, not in subspace anymore because the equations are really nonlinear, but to some submanifold. And where you are going to end up at this submanifold, that is being determined by the initial condition. Yeah. So qualitatively, it is very much like mass damper systems. Okay, I will skip the distributed parameter setting and just come to the final comments. Okay, there are many things that are being considered within this theory. And so we have this all these interconnected subsystems. And what is for many purposes important is that you are able to turn them into lower dimensional models. Yeah. And you can do that subsystem by subsystem, but then you need that you do it in a structure preserving manner. Yeah? But the low dimensional approximation is again Port-Hamiltonian. The same holds for if you go from infinite dimensional components to finite dimensional components. Okay, there is, in fact, although I was being introduced as somebody from nonlinear control, which is the case, but I did not say much about that. So there is also a whole story how you can exploit this structure of the system for control purposes. Yeah, so you are adding systems, controller systems, which can be also dynamical systems on their own. Yeah, like integral controllers and many more complicated things in order to influence the dynamics of the system, and so that you get some desired dynamics. Okay, so the summary of the talk is over here. So I hope that this leads to questions and discussion. I think that I have basically covered all the items which are being addressed over here. Let me just end by giving some references, especially the first one. You can just download it. That is an introductory overview, so that it should be easily accessible. Okay, thank you for your attention.
Time for questions.
So I understood that you can sort of work with dissipative systems, but if you have like an input of energy, you can also deal with that, like the dissipation, or is where?
No. Okay, so I should have emphasized that. Okay, I think the best is to go back to something that I only mentioned very briefly. Yeah, so the last line over here. Yeah. Okay, so because the Dirac structure is power conserving, so you get the DDT of H, which is the vector product of ES and FS, that or minus of it, is equal to these two terms. Yeah, where the first term is the energy dissipation, which is always less than or equal than 0. Okay, that is the sign convention that I'm using. And then the second term over here, yeah, that is the power that is flowing in or out by the interaction with the environment. Yeah, so due to the fact that I have energy dissipation, I always have this inequality, but I still have a term over here. And so I can still add energy to the system by the external port or get system out of the system, and by manipulating these variables, which can be thought of inputs and outputs.
It's as long as you have a net dissipation or net conservation.
No. I mean, so if okay, there are two complementary cases. One is that I look at it from a control point of view, where I look at them as being inputs and outputs. Yeah, and then I can manipulate the input in order that, well, either I extract energy or I put energy into the system. And the other complementary point of view is that these are variables which are being interconnected to another system. Yeah, and then it depends on the properties of that other system, how the energy is flowing, right?
Questions? Yeah.
Just to add on that, I mean, if you consider, say, a turbulent flow, then typically you have dissipation, but you also need energy input to keep it going. But that always balances. So in a sense, in a steady situation. So in a sense, then the dissipation depends on how much energy you put in.
Well, I think that what you are saying, that you are doing it on purpose, that you are.
This is the control already.
Right, so
Okay.
that you are,
Yeah.
that you are manipulating this in such a way on purpose that you just compensate for that. Yeah, that is, of course, that is a possible scenario, but it's not the only one. No?
More questions? Probably some final questions. Do you have some like advice for people, because a lot of people are now thinking about the control of complex systems. Do you have any advice for people how to avoid the pitfalls, like some common kind of problems that's in this area?
Pitfalls.
Yeah, how to avoid that?
Okay. Well, I mean, so like I mentioned a bit, is that most of my experience is in engineering systems, so technological systems, then which you build yourself, basically. Well, I mean, I do not do that, but other people do. But if you go to natural systems, things are, of course, even more complicated. But okay, so I'm not yet talking about pitfalls, but I think that what is very important in the modeling is that you first start with some simple subsystems. What are the phenomena? What are the basic phenomena, or that you have in mind, and that you then first put them together, and then secondly, it will always turn out that this is not exactly what you want, or it is in fact far from what you want. So, but this network modeling point of view, I think is nice, because you can do the modeling subsystem by subsystem. So you can look at libraries of models. Yeah. And then you can just, if you do not like the overall thing, then you can say, well, maybe there's a problem with the model for that physical phenomenon. So I take it out and I put a better one in it, more complicated. Yeah. Okay, so that's not yet about pitfalls. What are pitfalls? Well, now you're asking me, so I'm so convinced about this that I don't see any. But I mean, maybe there are people here in the audience who can point out what are the pitfalls.
But I think it's nice that you already showed the general ways, that's the how to do that, and also has this kind of theoretical framework to guide through the process. Yeah. So that's really nice.
Yeah, and what is also nice about this framework, so if you do modeling, you are often also not sure what kind of variables should I use. So this energy dictated way of modeling is also giving some structure to the modeling process.
Great, thank you.